Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today we are taking a look at the official Certified Kubernetes Administrator, or CKA Study Guide.
Right, and to set the stage for this, I want you to just picture this scenario. Imagine it's like 3 in the morning.
Oh, the classic nightmare.
Exactly. Your pager's just screaming at you. You grab your laptop, eyes barely open, and you log in to find the production cluster is completely unresponsive.
And there's no fancy graphical interface to save you.
Right. There's no helpful setup wizard. It is literally just you, a blinking cursor in a Linux terminal, root access, and a relentless clock ticking down while the business is just bleeding revenue.
It's terrifying. But that scenario, that is exactly the pressure cooker this certification is designed to simulate.
Yeah. And that is the crucial context we need to set right away for this deep dive. For anyone listening who might be used to, standard IT certifications, the CKA is a completely different animal.
It really is. I mean, you aren't sitting in some sterile testing center clicking A, B, or C on a multiple choice exam.
Hoping you memorized enough textbook definitions, right?
Exactly. You can't just memorize your way out of this. You are dropped into a live, heavily constrained terminal environment.
You're given a set of broken or empty clusters, and you are essentially told to build them, administer them, and fix them.
Yeah, it's a 120-minute, strictly performance-based gauntlet. You have to prove you can actually drive the heavy machinery, so to speak.
Which completely changes the entire paradigm of how you prepare for it. You cannot cram for this exam.
No, absolutely not. You have to build real muscle memory. And the guide we are dissecting today, it's massive and it's definitely intimidating.
But our mission here, in this deep dive, is to extract the absolute critical mechanics from all that material.
Right, because we're going to explore the underlying architecture, so you aren't just, rote memorizing syntax. You need to understand the physics of the system you're operating.
Because when things break under pressure, rote memorization totally fails. You need that solid mental model of how the components actually interact.
So true. So let's start right there with the pressure itself. Section 1 of our deep dive is conquering that 2-hour clock.
Yeah, time is absolutely your biggest enemy here. The guide makes that explicitly clear. You have 2 hours to solve 15 to 20 complex, hands-on administrative tasks.
And the passing score is 66%, right?
Yep, 66. And you are currently tested against Kubernetes version 1.3.
You do get access to official documentation, sure, but...
But if you stop to actually read a paragraph, you are already falling behind. You just don't have the time.
Exactly. So how do you construct a survival strategy for that kind of ruthless environment?
Well, you have to ruthlessly eliminate friction from the very first second you log in.
The guide heavily emphasizes environment optimization before you touch a single cluster component. You have to think about cognitive load.
Right, because every time you type a command, your brain is doing like micro-calculations.
And every typo requires you to stop, read a syntax error, hit the up arrow, find the misplaced character, and execute again.
Which sounds minor, but over 2 hours. Those seconds compound into minutes.
And those minutes are literally the difference between passing and failing.
So the guide is very prescriptive about this. It tells you to immediately set up aliases. Most famous one, of course, is mapping the primary command line tool.
Right, the classic alias, key, fee, kubectl.
Yeah. But, is it really just about saving keystrokes?
It's more about reducing the surface area for mistakes. Kubectl is just an awkward string of characters to type rapidly.
It really is. My fingers always trip over the CTL part.
Same. And if you type it 200 times during the exam and you make a typo on, say, 10% of those, you've just wasted valuable diagnostic time.
So by aliasing it to just K, you bypass that risk entirely. But you don't stop there, right?
Yeah.
You need to configure your shell environment to act as an active copilot.
You're talking about the bash completion script.
Exactly. You run the source command against the completion script provided by the tool itself.
But here's the catch. Because you alias the tool to K, you also have to use the complete command to bind that auto-completion to your new alias.
Right. Otherwise, the terminal doesn't know K means the same thing.
Once you do bind it, the terminal becomes aware of the cluster state. It's like magic.
So if you type K get pod and hit tab, what happens?
It will literally query the cluster and list the available pods, or auto-complete the name of a specific pod for you.
That is huge. You are no longer relying on your short-term memory to remember if a deployment was named, like frontend v1 or frontend v2.
Exactly. The environment just tells you. That shifts the mental burden entirely off the operator and onto the machine.
Which is exactly what you need. But there's an even bigger trap the guide warns about. And it involves how you actually create resources.
Oh, writing YAML from scratch.
Yes. If I need to deploy a complex web application, my instinct as an engineer might be to just open Vim, create a blank YAML file, and start writing.
Writing the API version, the kind, the metadata, the spec, all from memory. Doing that under a ticking clock is a guaranteed way to fail.
It really is. The Kubernetes API is so deeply nested and highly specific.
One missed space or, one misaligned indentation, and the API server will straight up reject your file.
And you just do not have time to debug your own YAML formatting. So what's the alternative?
The guide strongly advocates for imperative commands using the dry run flag.
Okay, let's break down the mechanics of this because it's honestly fascinating. You use dry run client OYAML.
Right.
What is functionally happening under the hood when I append that to a creation command?
Well, when you execute a standard imperative command, like telling the system to create a deployment, the tool constructs a JSON payload.
And it sends it to the cluster's API server to be executed, right?
Yeah, exactly. But when you add dry run client, you are intercepting that process.
You're putting up a roadblock.
Yeah. You are telling the tool, build the payload, ensure the syntax is completely valid against the API schema, but do not actually send it to the cluster.
And then the OYAML flag comes in.
Yep. That flag says, instead of executing this, just print the perfectly formatted YAML structure to my standard output.
Wow, so you are basically weaponizing the tool to write the boilerplate code for you.
Exactly. You redirect that output into a file, open it in your text editor, and suddenly you have a syntactically perfect template.
And then you just tweak the 2 or 3 specific fields the exam question asked for, like maybe adding a specific label or changing a port.
And then you apply it. It is the only way to operate efficiently in this exam.
Because you're moving from a state of creation to a state of modification, which is just vastly faster and safer.
And to further reduce cognitive load, you have to leverage the allowed documentation strategically.
Right, you don't use it to learn on the fly.
No, you use it as a clipboard. The guide suggests having specific, hard-to-memorize configurations already bookmarked.
Like the YAML for persistent volume, or maybe a really complex network policy.
Exactly. When a question demands it, you navigate straight to the bookmark, copy the block, paste it into your editor, and just modify the values.
So hearing all this, I've got an analogy. It sounds like stepping into the exam isn't really about being a student taking a test.
What is it then?
It's like a timed escape room. You don't try to forge a key from scratch out of raw metal while the clock is ticking down.
Ha! That's a great way to put it.
You use the tools lying around, the imperative commands, to hack your way out. You build that safety net in the first 5 minutes.
So that when the real work begins, your mental bandwidth is entirely freed up to focus on the architecture itself.
And that architecture is complex, which transitions us perfectly into the absolute core of the exam.
Section 2. Cluster architecture, installation, and configuration, which is 25% of your total score.
Let's pull back the curtain on this. When we say Kubernetes, we sort of throw around this monolithic term, but it's not a monolith at all.
Not even close. The guide breaks it down into a highly distributed, decoupled system.
It essentially splits the world into 2 domains. The control plane, which makes the decisions, and the worker nodes, which actually run the applications.
Right. And for the CKA, you have to understand the specific role of every single binary running in both of those domains.
Let's look at the control plane first. This is the brain trust.
And the absolute center of that universe, the component that everything else revolves around, is the Kube API server.
Now, I often hear people try to simplify the Kube API server as just a gateway or a router.
Yeah, that's a common misconception.
But reading through the underlying mechanics in the guide, it acts a lot more like a highly secure, incredibly strict air traffic control tower.
That is a much more accurate model. The Kube API server is a RESTful API endpoint, and it is the only component in the entire cluster that is allowed to communicate with the cluster's database.
Literally the only one.
Literally the only one. Every other component, whether it's a user on a laptop, a worker node reporting its health, or an internal controller, must submit an HTTP request to the Kube API server.
So it's the ultimate bouncer.
Exactly. It authenticates you, it checks if you have the authorization to perform the action, and it runs your request through admission controllers.
Just to ensure it meets all the cluster policies, right?
Yep. And only after all of that does it actually record the change.
And the place it records that change is etcd. The guide describes etcd as a strongly consistent, highly available key value store.
Which is the memory bank of the cluster.
But I want to push back on the architecture here for a second just to play devil's advocate. Why not just use a traditional relational database like Postgres or MySQL?
It comes down to the fundamental design philosophy of Kubernetes, which is declarative state reconciliation.
Meaning what exactly in this context?
Well, a relational database is great for complex queries and joining data, but Kubernetes doesn't really need to join data.
Oh, I see.
It needs an ultra-fast, absolutely reliable record of what the desired state of the cluster is versus the actual state.
So it's all about speed and consensus.
Exactly. etcd uses the Raft consensus algorithm. So if you have a highly available control plane with 3 ESCD nodes, they constantly vote on the state of the data.
And if one node goes down, or its data gets corrupted,
The other two maintain the quorum and keep the cluster running seamlessly. The latency requirements are incredibly strict here.
how strict are we talking?
We are talking about disk sync operations measured in single-digit milliseconds.
Wow.
Because if etcd slows down, the entire cluster's ability to react to changes just grinds to a halt.
Okay, so the API server handles the traffic, and etcd holds the absolute truth. But neither of those components actually does any work regarding the applications, do they?
No, they just store and validate records. The entity that actually makes decisions about where things go is the scheduler.
Ah, the Kube scheduler. The guide makes it sound like a fascinating piece of software.
It really is. It basically runs as a continuous loop, just constantly watching the Kube API server for new pods.
Pods that have been created but don't have a node name assigned to them yet.
Exactly. When it spots an unscheduled pod, it runs a two-phase operation, filtering and scoring.
Walk me through those phases, because I know the exam heavily tests the edge cases of why a pod might fail to schedule.
Sure. In the filtering phase, the scheduler looks at the pod's requirements. Let's say it needs 2 gigabytes of RAM and a node with a GPU.
Okay, hard constraints.
Right. It filters out every single worker node in the cluster that cannot physically meet those hard constraints.
And if no nodes survive that filter,
Then the pod stays in a pending state indefinitely. It just sits in the waiting room.
got it. But if multiple nodes do pass the filter, then what?
Then the scheduler moves to the scoring phase. It applies a mathematical weight to the remaining nodes based on soft constraints.
Like what kind of soft constraints?
Maybe one node already has the necessary container images cached locally, so it's faster to start. Or maybe the scheduler is trying to spread pods across different physical availability zones for fault tolerance.
So it scores them all, picks the node with the highest score, and then what? Just tells the node to run it?
No, it submits a binding request back to the Kube API server to officially assign the pod to that node's record in etcd.
Oh, right, because everything has to go through the API server.
Exactly.
Okay, so the scheduler finds a home. Then we have the Kube controller manager. The guide lists this as the component running all the core control loops.
Yeah, if the API server is air traffic control and the scheduler is the logistics planner, the controller manager is the tireless factory floor manager.
I like that. It doesn't push commands, it observes, right?
Exactly. It runs dozens of independent control loops, like the node controller, the replica set controller, the endpoints controller.
And each loop is just constantly comparing the desired state stored in etcd with the actual state of the cluster.
Right. So if you declare that you want 5 web servers running and a worker node suddenly loses power and takes 2 of those servers offline,
The replica set controller notices the discrepancy.
yep. But it doesn't try to fix the broken node. It simply tells the API server, I need 2 new pods to replace the missing ones.
And then it relies on the scheduler to place them somewhere else.
Exactly. It's a team effort.
You know, this declarative model is honestly the hardest mental shift for people coming from traditional imperative scripting.
Oh, absolutely.
You don't tell the system how to fix itself. You just declare the end goal. And the system's controllers work tirelessly to make reality match your declaration.
It requires a lot of trust in the system.
It really does.
Yeah.
Now, that covers the control plane. Let's move out to the actual workhorses. The worker nodes. The guide highlights the kubelet, the container runtime, and kube proxy.
Right. The kubelet is the primary agent running on every single worker node. It's basically the bridge between the node's physical hardware and the control plane.
And it just watches the Kube API server for its own name, essentially.
Yes, it looks for any pods that the scheduler has assigned to its specific node. When it sees a match, it takes the pod specification and begins the process of actually manifesting it.
But the kubelet doesn't actually run the containers itself, does it?
No, the kubelet is a manager, not an engine. It takes the spec and communicates over a local socket to the Container Runtime Interface, or CRI.
And the runtime, which the guide notes is typically containered in a modern 1.3 cluster, is the low-level engine doing the heavy lifting.
Right. The runtime actually pulls the image from a registry, unpacks it, interacts with the Linux kernel to set up the isolated namespaces and control groups, and starts the process.
And then the kubelet just monitors the health of that process and continuously reports the status back to the API server.
You got it. And rounding out the node components is kubeproxy, which handles the network routing rules on the local machine.
So that traffic can actually find these dynamic, ever-changing containers. We'll definitely dive deep into networking later, but it is essential to know that kubeproxy lives on every single node.
Exactly. So we know the components, but here's the kicker. The CKA expects you to be able to build this entire distributed system from a blank slate.
Using a tool called kubeadm.
Yes. Cluster installation is a massive practical component of the exam. You are given raw Linux servers and expected to bootstrap a secure, functioning control plane and attach worker nodes to it.
The guide's prerequisite checklist for kubeadm highlights something that I know trips up a lot of seasoned sysadmins.
Oh, disabling swap memory.
Yes. You have to run sudo swap off HA, and you have to actually remove swap from the file system table so it doesn't come back on reboot.
Because if you leave it on, the kubelet will literally refuse to start.
But why does Kubernetes take such a draconian stance against swap memory? Traditional Linux systems rely heavily on swap to prevent crashing when RAM fills up.
It is entirely about predictability and the physics of resource allocation. Kubernetes relies on the scheduler to place pods based on the actual physical memory available on a node.
Right, you uses Linux control groups or T-groups to strictly enforce the memory limits of a container.
Exactly. So if a container asks for 1 gigabyte of RAM, the pick group ensures it gets cut off if it tries to use more.
But think about what happens if swap is enabled.
If a node's physical RAM fills up, the Linux kernel will silently start paging memory blocks to the hard drive to the swap space.
And the container has no idea. It thinks it is still running in memory, but it's actually reading and writing to a spinning disk or a solid-state drive.
And the performance of that application will absolutely tank. Disk I/O is orders of magnitude slower than RAM.
And from a troubleshooting perspective, that is a nightmare.
It is. Kubernetes' philosophy is that it is much better for a container to hit its true memory limit and be mercifully killed and restarted by the OM killer, the out-of-memory killer, than to silently suffer catastrophic performance degradation that is nearly impossible to debug.
So disabling swap forces an honest accounting of physical resources. It makes perfect architectural sense when you frame it like that. You are forcing failures to be loud and immediate rather than slow and silent.
Exactly. So you disable swap, you install the container runtime, you install the kubelet in kubeadm, and then you run kubeadm init on the master node.
Which generates this massive cryptographic infrastructure, starts the control plane components as static pods, and hands you a join command token.
You run that token on the worker nodes, and suddenly they are part of the cluster.
It sounds almost magical when you build it. But the exam also heavily tests the lifecycle management, specifically cluster upgrades.
Yes, and the guide outlines an aggressively strict multi-step sequence for upgrading a node.
You cannot take shortcuts here. You must upgrade the control plane nodes first, and then the worker nodes.
And you cannot simply run a package manager update on a live node. The exam demands you follow the cordon and drain lifecycle.
I want to challenge this process for a second. If we are running modern stateless microservices that are designed to handle failure, why do we need this delicate multi-step dance?
What do you mean?
Like, why can't we just upgrade the kubeadm binaries, restart the kubelet in place, and let the applications experience a momentary blip while the service restarts?
Well, because you are assuming the applications are purely stateless, and that a momentary blip is acceptable to the business.
Right, which isn't always true.
In an enterprise environment, a node might be running a critical batch job halfway through processing, or a stateful database replica synchronizing data.
You can't just violently pull the rug out from under those workloads without risking data corruption.
Exactly. It's like aviation. You can't replace the engine of a plane mid-flight. You have to shift the passengers, which means draining the pods to other nodes. Then you do the maintenance, the upgrade, and open the gates again.
Uncoordinate.
Ah.
Okay, let's trace the mechanics of this elegant shift. What is the actual command sequence?
First, you cordon the node. You use the command to mark the node as unschedulable.
When you do this, you are updating the node's metadata in the API server, right?
The scheduler instantly sees this flag and says, under no circumstances will I assign any new pods to this machine.
However, cordoning is purely passive. The pods currently running on the node are left completely untouched. They continue serving traffic.
Right. We have stopped the influx, but the node is still fully loaded. The active step is the drain command.
This is where you actively shift the workloads.
When you run a drain, the system uses the eviction API. It politely sends a termination signal to the running pods, giving them a grace period to finish their current requests and shut down cleanly.
And as they terminate, the replica set controller notices the pods are gone and immediately spins up replacement pods on other healthy worker nodes.
Exactly. But the guide specifies that you often have to use specific flags to force a drain to succeed. Flags like ignore daemon sets and delete empty dir data.
Why does the drain command stall without them?
Because the drain command is inherently cautious. If you have a daemon set running, which is a pod designed to run on every single node, like a network plugin or a log forwarder, you cannot evict it to another node.
Because that other node already has its own copy of the daemon set.
Right. So you have to explicitly tell the drain command, ignore the daemon sets, I know they will stay behind.
Makes sense. And what about the empty dir flag?
Similarly, if a pod is using an empty dir volume, it means it has ephemeral data stored locally on that specific physical hard drive.
So if you evict the pod, that local data is permanently destroyed.
Yes, and the drain command will halt and refuse to proceed unless you explicitly acknowledge that data loss by passing the delete empty dir data flag.
So you have safely evacuated the node, the workloads are humming along on other machines. Now you do the actual maintenance. You upgrade the tool, apply the upgrade the kubelet, and restart the system service.
And once the node comes back online and reports its upgraded version to the API server, you issue the final command. You uncoordinate.
You remove the unschedulable flag, opening the gates for the scheduler to start assigning pods to this fresh, upgraded machine. It is a seamless migration of state.
That sequence really highlights the orchestration power of the platform, but there is another administrative task in this domain that carries catastrophic stakes.
Oh, etcd, backup and restore.
Yes. We established earlier that etcd is the brain. All the declarative configurations, all the secrets, all the state that lives there.
If the etcd volume gets corrupted and you have no backup, what happens?
Your cluster is completely destroyed.
Wow. Even if the worker nodes are still running.
The workloads might temporarily continue running on the worker nodes because the kubelets keep their local processes alive, but you have lost all ability to manage them, scale them, or route new traffic to them.
It is a total control plane failure. Taking a snapshot of etcd is a guaranteed exam scenario, and it is entirely cryptographic.
Let's unpack the cryptography. The tool is etc.html, and you have to enforce API version 3 by prepending etcd cdti eti 3 to your command.
But you can't just tell it to take a snapshot, right? You have to provide a litany of certificates.
Because etcd is the most sensitive component in the architecture. It is locked down via mutual TLS or MTLS. It doesn't just encrypt data in transit, it demands cryptographic proof of identity before it accepts any command.
So to take a snapshot, you must pass the endpoints flag to specify which node you are targeting. Then you must pass the CACert to verify the certificate authority.
Then you must provide your client certificate with the cert flag and your private key with the key flag.
The guide notes, these are usually located deep in the file system, typically under a Kubernetes BSD.
So during the exam, you're essentially forging the identity of the API server itself to extract the snapshot directly from the database.
Exactly. And restoring it is just as rigorous. You use the snapshot restore command, but you don't overwrite the existing corrupted database.
No, you define a brand new data directory for the restored files to unpack into. Then you have to modify the etcd static pod manifest file, updating its configuration to point to that new directory path.
And when you save the file, the kubelet automatically detects the change, restarts the etcd pod, and the cluster's brain comes back online with the historical data.
The overarching theme here is authorization and identity. Who is allowed to do what? Which brings us to the final piece of the architecture domain, RBAC, or role-based access control.
The exam expects you to intimately understand the boundaries of permission. The guide draws a very hard line between namespace scope permissions and cluster scope permissions. Let's start with namespaces.
Think of a namespace as a virtual cluster carved out of your physical cluster. You might have a physical cluster with 100 nodes, but you can create a development namespace and a production namespace.
An RBAC allows you to tightly constrain an identity, like a user or a service account, to a specific boundary within those namespaces.
The text uses the example of granting a user access, say, pod reader access, in the development namespace. To achieve this, you need two distinct objects. a role and a role binding.
Why do we need both? Why not just assign the permissions directly to the user?
Because decoupling the rules from the subjects allows for massive scalability. A role is purely a definition of actions.
So you create a role that says, allow get, list, and watch verbs on the pod's resource.
Exactly. It doesn't care who is performing those actions. The role binding is the bridge. It connects that predefined role to a specific subject within that specific namespace.
So if you later hire 10 more developers, you don't write new rules, you just add them to the existing role binding.
Yep. But the limitation is that a role only operates within its designated namespace. If the user tries to list pods in the production namespace, the API server's authorization module just blocks the request.
Precisely. And this is where cluster roles come in. Some resources in Kubernetes are not bound by namespaces at all.
Worker nodes are a great example. A node doesn't belong to a namespace. It belongs to the whole cluster. Persistent volumes are cluster-wide too.
If you need to grant someone permission to list all nodes, or if you want to grant a user permission to list pods across every namespace simultaneously, a standard role will fail.
You must elevate to a cluster role, which defines the global permissions, and a cluster role binding, which attaches the user to that global scope.
But the exam will intentionally try to trick you by asking you to grant permissions for a cluster-scoped resource using a namespace scope role, and you have to recognize the architectural mismatch.
Exactly. Understanding that boundary is absolutely critical for security and administration.
So if we synthesize everything we've covered so far, we have secured our terminal environment, we understand the components of the control plane and worker nodes, we have bootstrapped the cluster.
Managed its life cycle through upgrades, backed up its database, and locked down access via RBAC.
We have a pristine, highly available infrastructure. But an infrastructure without applications is just expensive, idle silicon. We need to actually run workloads.
Which brings us to section 3 of our deep dive. Running the show, workloads and scheduling, which accounts for 15% of the CKA exam.
Workloads are the entire justification for the infrastructure's existence. And Kubernetes provides several different controllers to manage the life cycle of these workloads, depending on the architecture of the application.
The guide highlights deployments, daemon sets, and stateful sets. Let's start with deployments. They are ubiquitous.
The guide refers to them as declarative updates for pods. But a deployment doesn't actually manage pods directly, does it? There's a layer of abstraction beneath it.
That's a vital architectural detail. A deployment actually manages a replica set, and the replica set manages the pods.
This layered approach is what enables seamless zero-downtime rollouts. Right.
Exactly. When you submit a deployment YAML specifying you want 3 replicas of an Nginx web server using version 1, the deployment controller creates a replica set. The replica ensures 3 pods are running.
But the power really comes when you need to update that application to version 2. What happens under the hood?
When you update the image version in the deployment specification, the deployment controller does not just delete the old pods and start new ones. That would cause a massive outage.
Right.
Instead, it creates a brand new replica set for version 2. It then begins a mathematical rolling update based on 2 parameters: max surge and max unavailable.
Let's define those, because I know tweaking those values is a very common exam requirement.
Max surge defines how many extra pods the system is allowed to spin up above your desired replica count during an update.
Okay, and max unavailable.
That defines how many pods are allowed to be offline during the update. So the controller will spin up one version 2 pod in the new replica set, wait for it to report healthy, and then spin down one version 1 pod in the old replica set.
It slowly scales the new one up and the old one down, shifting the traffic seamlessly.
And if the new version crashes on startup, the rollout halts automatically, preventing the broken code from taking down your entire fleet.
It is an incredibly resilient mechanism for stateless applications. But what if the application isn't stateless? What if it is a foundational piece of infrastructure that needs to be present on the actual hardware?
That's where the guide points to daemon sets. A daemon set fundamentally alters the scheduling paradigm.
Right, because in a deployment, the scheduler decides where the pods go based on available resources. You might have 3 replicas, all end up on the exact same worker node if that node has enough capacity.
But a daemon set ensures that exactly 1 copy of a pod runs on every single eligible node in the cluster.
The classic use cases are log forwarders like Fluent or network monitoring agents. You need those services running on every piece of hardware to capture the telemetry of the entire system.
Exactly. And the magic of a daemon set is its dynamic nature. If you add a brand new empty worker node to your cluster on a Tuesday, the daemon set controller instantly detects the new hardware and spawns the agent pod on it without any human intervention.
It ensures a baseline state across your fleet. So deployments are for stateless scalability, and daemon sets are for blanket coverage. That leaves stateful sets.
The guide mentions these are for applications requiring stable identity and storage. This implies that regular pods lack stability.
Regular pods are entirely ephemeral. If a pod in a deployment dies, the replica set creates a new one. That new pod will have a completely random, dynamically generated hash in its name, and it will likely be scheduled on a different node.
For a stateless web server, that doesn't matter at all. But imagine running a distributed database like Cassandra or a MongoDB replica set.
Right, the database instances need to know who the primary is, who the secondaries are, and they need to reconnect to the exact same data volume if they crash. A random name and random storage is catastrophic.
This is exactly what a stateful set solves. Instead of random hashes, a stateful set provides strict, ordered, sequential naming.
So if you ask for 3 replicas, they will be named DB0, DB1, and DB2.
And they're started in strict order, one after the other. If DB1 crashes, the controller does not create a new pod with a random name. It meticulously recreates DB1.
And it maintains its network identity too, usually coupled with a headless service. So other applications can hard-code a connection string to DB1's specific DNS record, and even if the pod dies and restarts on another node, the network identity remains constant.
And critically, it maintains its storage identity. Stateful sets use volume claim templates. Every pod gets its own unique persistent volume.
When DB1 is recreated, it is automatically reattached to the exact same physical storage drive it was using before the crash.
It provides the predictability of traditional virtual machines while retaining the orchestration power of Kubernetes.
Now here is a concept from the study guide that always feels like a backdoor in the architecture. Static pods. We just spent 20 minutes discussing how the API server processes requests, how the scheduler assigns pods, and how the kubelet runs them.
But the guide explicitly states that static pods completely bypass the API server and the scheduler. They go rogue.
How and why does this exist?
It exists to solve the ultimate chicken and egg problem of bootstrapping a cluster. We know that the control plane components, the API server, the scheduler, the controller manager, run as pods themselves in modern deployments.
Right.
But if the API server and the scheduler are pods, who tells the kubelet to start them? You cannot submit a pod manifest to an API server that isn't running yet.
You need a way to launch a pod without asking permission from the central authority.
Exactly. A static pod is managed directly, exclusively by the local kubelet on a specific node. When you configure the kubelet, you point it to a specific directory on the file system, typically a Kubernetes manifests.
And the kubelet runs a continuous watch loop on that folder.
Yep. If you drop a YAML file into that folder, the kubelet bypasses all central authority and immediately starts the container locally.
That is how kubeadm bootstraps the master node. It drops the manifests for the control plane into that folder. The local kubelet wakes up, sees the files, and spins up the API server.
Yeah.
Once the API server is up, the rest of the cluster can begin communicating.
Precisely. And it's important to note that while static pods bypass the API server for creation, the kubelet actually reaches out to the API server afterward and creates a mirror pod.
A mirror pod.
Yes, it's a read-only representation of the static pod so that if an administrator runs CAG get pods, they can still see that the component is running even though they cannot manage it via the command line.
Oh, that's clever. So if an exam question asks you to modify a static pod, you cannot use imperative commands.
Yeah.
You must SSH into the specific node, find the manifest directory, and edit the YAML file directly on the disk.
That is a critical administrative distinction you have to know. Okay, let's pull back to standard pods and talk about scheduling mechanics. We know the scheduler looks for capacity, but as administrators, we often need to force the scheduler's hand.
We need workloads to land on specific hardware. The guide covers node selectors, node affinity, and taints and tolerations. I want to contrast affinity and taints because they represent opposite forces in the cluster. Let's look at affinity first. Affinity is basically magnetism. It's an attractive force.
Yes. If you have a subset of worker nodes with solid-state drives, you label them disks. You then write a node affinity rule in your pod specification that says, I have an affinity for nodes with the label disk set.
The scheduler evaluates that rule. But the guide highlights that affinity comes in 2 flavors, hard and soft.
The hard constraint is formally called required during scheduling, ignored during execution. It is an absolute demand.
If the pod requires an SSD node and all the SD nodes are full, what happens?
The pod will remain in a pending state indefinitely. It will not compromise.
And the soft constraint.
That's preferred during scheduling, ignored during execution. It is a request. The pod tells the scheduler, I would strongly prefer an SSD node. Please try to score them higher. But if they are all full, I will settle for a standard hard drive node just to get running.
It provides flexibility for workload placement. So affinity acts as a magnet, drawing pods in based on their properties. Taints and tolerations are the exact inverse. They are a repulsive force applied to the node itself.
Think of a taint as a bouncer at a club and a toleration as the VIP pass. You apply a taint to a worker node. By doing so, you are telling the scheduler, do not put any pods on this machine unless they explicitly possess the matching toleration key in their manifest.
This is how the master nodes are protected from running standard workloads, right? CubeADM applies a default taint to the control plane nodes, so developers don't accidentally deploy their web apps onto the machines running the critical databases.
Exactly. And the guide expects you to master the 3 specific effects a taint can have. No schedule, prefer no schedule, and no execute. Let's break down the mechanics of each. No schedule is a strict blockade for new arrivals.
If a pod lacks the toleration, the scheduler will not place it on the node.
Right. However, it is not retroactive. If you apply a no schedule taint to a node that already has 50 running pods on it, those 50 pods are completely unaffected. They are allowed to stay indefinitely.
Okay, so it only stops new traffic. What about prefer no schedule?
That is the soft blockade. The scheduler will make every attempt to keep untolerated pods away from the node, but if the rest of the cluster is completely starved of resources and there is absolutely nowhere else to put the pod, the scheduler will bypass the taint and schedule it anyway. It's a suggestion, not a rule.
And that brings us to no execute. This one feels violent.
It is immediate and aggressive. No execute not only blocks new pods from scheduling, but it actively evaluates all the pods currently running on the node.
If any existing pod lacks the matching toleration, the bouncer steps in.
The kubelet will immediately begin evicting it and terminating its processes.
That is incredibly powerful. You could use a no-execute taint to rapidly evacuate a node that is experiencing hardware degradation without having to manually run a drain command on every workload. But managing where pods land is only half the battle. The other half is managing what they consume once they get there.
The final part of the scheduling domain is resource management, and this is where the Linux kernel internals really surface. The guide emphasizes the distinction between requests and limits.
Now, this is how you prevent a single runaway application from consuming all the CPU and RAM on a physical server and crashing the node. Let's define the terms. A request is a baseline guarantee, correct?
Yes. The request is primarily for the scheduler. If a pod requests 500 millicores of CPU and 1 gigabyte of RAM, the scheduler looks at the total capacity of the nodes and subtracts the sum of all existing requests.
It will only place the pod on a node if that node has unreserved capacity to guarantee that request. But the request doesn't actually stop the pod from using more, does it?
No, the request is just a calculation. The limit is the enforcement mechanism. And the way limits are enforced differs fundamentally between CPU and memory.
Right, CPU is considered a compressible resource.
If you set a CPU limit of 1 core, and your application tries to spike and use 2 cores to process a massive influx of data, the Linux kernel will not kill the process. It will simply throttle it.
It uses at-group quotas to artificially restrict the CPU cycles the process receives, slowing the application down but keeping it alive. But memory is not compressible. If you need memory, you need it.
Exactly. Memory is incompressible. If you set a memory limit of 1 gigabyte and your application has a memory leak and tries to allocate 1.1 gigabytes, the Linux kernel intervenes lethally.
The killer instantly terminates the container process. The pod status will show an killed error, and it will be restarted by the kubelet.
This is a vital operational concept. If an administrator is troubleshooting a pod that keeps crashing with killed, they don't necessarily have a Kubernetes problem. They have an application profiling problem or an improperly configured limit.
And to manage this at scale, the exam covers limit ranges, which automatically inject default requests and limits into every pod deployed in a namespace, and resource quotas, which act as a total ceiling for a namespace.
You can use a resource quota to ensure the development team can never consume more than a total of 10 cores across all their pods combined, protecting the rest of the cluster from noisy neighbors.
So we have highly orchestrated workloads. They are perfectly scheduled across the nodes, they are respecting their resource limits, and they are resilient to node failures. but isolated pods are essentially useless.
If a web front-end cannot communicate with its back-end database, or if a customer on the internet cannot reach the front-end, the system has failed its primary objective.
This requires us to explore the network architecture. Let's transition to Section 4, connecting the dots. Services and networking, which represents 20% of the exam.
Networking in Kubernetes is notoriously intricate because it operates on multiple conceptual layers simultaneously. You have pod-to-pod communication, internal service discovery, and external ingress routing. But the fundamental challenge Kubernetes networking solves is the ephemeral nature of pods.
Right, pods are cattle, not pets. They die, they scale up, they shift to different nodes, and every time they restart, they get a completely new random IP address from the container network interface.
You cannot hardcode a pod IP address into an application configuration because that IP address might not exist 5 minutes from now.
This is why the service abstraction is the cornerstone of cluster networking. A service provides a stable, permanent virtual IP address and a permanent DNS name. It acts as a static anchor for a highly fluid set of back-end pods.
The mapping mechanism between the static service and the dynamic pods is crucial. It uses label selectors.
Exactly. When you create a service, you define a selector, for example, app database. The service doesn't care what the pod's IP address is or what node it is on.
The controller continuously queries the API server for any healthy pods bearing the label app database. As pods spin up and get IP addresses, the service automatically discovers them, adds those IPs to an internal endpoints object, and begins load balancing traffic across them.
The guide details 3 main service types that escalate in complexity: cluster IP, node port, and load balancer. Let's unpack the mechanics of each. The default is cluster IP.
Cluster IP is strictly for internal east-west traffic. It assigns a virtual IP from a reserved internal subnet. If you deploy a back-end microservice that only needs to be accessed by other microservices within the same cluster, you expose it via a cluster IP.
It is completely inaccessible from the outside network. But how does that virtual IP actually route traffic? It's not a real network interface on a router.
It relies on kubeproxy. Remember the component we discussed earlier that lives on every worker node? Kubeproxy watches the API server for new services and endpoints.
When you create a cluster IP, kubeproxy immediately writes dozens of complex IP tables or IPVS rules directly into the Linux kernel of every single worker node.
When a pod tries to send a packet to that virtual IP, the kernel intercepts it, uses the IP tables rules to rewrite the destination address to one of the actual physical pod IPs, a process called Destination Network Address Translation, or DNAT, and forwards the packet on.
That is a brilliant abstraction, but it doesn't solve external access. If I have a public-facing web application, a cluster IP is useless to a customer on a web browser. The next escalation is a node port service.
A node port service punches a hole in the perimeter. When you create a node port, Kubernetes allocates a specific high-numbered port, always in the range of 30,000 to 322,767.
It then configures kubeproxy to open that exact port on the physical public-facing network interface of every single worker node in the entire cluster.
So if my cluster has 50 nodes and the node port is 31200, a customer can send an HTTP request to the public IP of any of those 50 nodes on port 31200, and the traffic will enter the cluster.
Yes. Once the traffic hits the physical node, the IP tables rules take over, routing it inward to the service's virtual IP, and then finally load balancing it to the underlying pods, even if those pods are running on completely different nodes.
But practically speaking, asking a customer to append a 5-digit port number to a URL is not viable for production.
Which is why node port is primarily a building block. For true production traffic, you use a load balancer service. How does a load balancer service interact with the underlying infrastructure?
It requires integration with a cloud provider's API. If you create a load balancer service on AWS or Google Cloud, Kubernetes provisions a node port behind the scenes.
But then, the Cloud Controller Manager reaches out to the AWS API and dynamically provisions an actual physical network load balancer in the cloud.
It configures that cloud load balancer to listen on standard port 80 or 443 and routes the traffic down into the specific node ports on your worker nodes. It automates the external infrastructure provisioning.
Now, this architecture works perfectly for routing TCP and UDP traffic at layer 4. But the guide heavily emphasizes the ingress resource, which operates at an entirely different layer of the OSI model. Why do we need an ingress if we already have load balancers?
Cost and routing intelligence. If you have 20 different microservices, say an API, a billing portal, and a blog, and you expose each one with a load balancer service, you are asking the cloud provider to provision 20 distinct physical load balancers.
That becomes astronomically expensive. Furthermore, a Layer 4 load balancer only understands IPs and ports. It doesn't know what an HTTP path is. It cannot look at a URL.
So an ingress operates at layer 7. It inspects the HTTP request itself.
Exactly. An ingress allows you to consolidate all your external traffic behind a single IP address and a single cloud load balancer. You define routing rules based on host names and paths.
You can write an ingress rule that says, if the HTTP request is for mydomain.com as a PI, route it to the backend APA service. If the path is blog, route it to the blog service. It acts as a highly intelligent, programmable reverse proxy.
But the ingress object itself is just a YAML file with a set of rules. The guide notes that creating the YAML does absolutely nothing unless you have an ingress controller installed in the cluster to execute those rules.
The controller is the actual software engine doing the work. The most common one is the Nginx ingress controller. It runs as a pod within the cluster.
It constantly watches the API server for any new or modified ingress YAML files.
When it sees your new routing rules, it parses the YAML, translates it into an actual nginx.conf file, dynamically hot reloads the Nginx process inside its container to apply the new configuration, and begins proxying the traffic according to your paths. It also handles SSL termination, decrypting the HTTPS traffic before passing it internally.
The exam heavily tests writing these ingress definitions, so knowing the syntax for path types like prefix versus exact is crucial. Now, I want to address a massive security implication in the default networking model.
Oh, the flat network.
Yes. The text highlights that by default, Kubernetes cluster networking is completely flat and open. Any pod in any namespace can communicate with any other pod without restriction. A compromised front-end container in the development namespace can freely send packets to a critical production database container. Why would a platform designed for multi-tenant enterprise orchestration default to a zero-trust nightmare?
It is a historical compromise favoring developer velocity. In the early days of Kubernetes, the primary goal was to make microservice orchestration as frictionless as possible. If developers had to spend hours configuring complex firewall rules just to get two pods to talk, adoption would have stalled.
The flat network means it just works out of the box. But you're absolutely correct. In a production environment, an open network is unacceptable for compliance and security.
This is where network policies come in. They act as software-defined firewalls. The exam expects you to know how to lock down a namespace.
Network policies fundamentally alter the default stance of a pod. The moment you apply a network policy that selects a specific pod, that pod becomes isolated.
The stance flips from default allow to default deny. All incoming and outgoing traffic is immediately dropped at the network interface level.
And from there, you have to write explicit declarative rules to punch holes for legitimate traffic.
Yes. You write ingress rules specifying exactly which namespaces or specific pod labels are allowed to send traffic in on which specific ports. And you write egress rules defining exactly what external IP blocks or internal services the pod is allowed to talk to.
A classic CKA exam task is to write a default deny-all policy for an entire namespace, effectively severing all unapproved communication and then carefully restoring access for a specific web application.
And just like ingress, network policies require a specific engine to enforce them. You have to be using a container network interface plugin that supports them, like Calico or Cilium, which use advanced Linux features like eBPF to enforce these packet drops efficiently before they ever reach the container.
Finally, underlying all this routing and policy enforcement is DNS. The guide explicitly lists core DNS. If core DNS fails, the services might be perfectly healthy, but the cluster goes blind.
Core DNS is the internal phone book of the cluster. Whenever you create a service, Core DNS automatically generates a fully qualified domain name record for it. If a pod needs to talk to the database service, it doesn't query an IP, it queries the hostname.
Core DNS intercepts that query, translates it to the service's virtual IP, and the traffic flows. Diagnosing DNS resolution issues from inside a running container is a vital operational skill we will tackle in the troubleshooting section.
So we have established a highly resilient, secure network. Data is flowing gracefully between microservices, but there's an existential problem with containers that we have to solve before we can run a true production database.
Containers are inherently ephemeral. When a pod is deleted, the container is destroyed. The isolated file system inside that container evaporates into the ether. Any data written to it is permanently lost. How do we keep data alive when the compute layer is constantly dying?
This takes us to Section 5 of our deep dive, keeping it real with storage, which makes up 10% of the exam. Storage in Kubernetes is fundamentally about decoupling. You have to separate the lifecycle of the data from the lifecycle of the compute pod.
The guide begins by examining ephemeral storage options, specifically empty dir and host path. These do not decouple the data. They are tied to the immediate physical environment. Let's use a physical analogy here. Think of a pod as a guest renting a hotel room.
Okay, I like this.
An empty dir volume is like the small temporary safe in the hotel room closet. When the guest checks in, the safe is empty. While they're in the room, they can put things in it. In a pod, an empty dir is incredibly useful for sharing temporary data between multiple containers running inside the exact same pod. For instance, an application container writes logs to the empty dir, and a sidecar container reads those logs and forwards them to a central dashboard.
That's a perfect use case. But the critical limitation is the life cycle.
When the guest checks out, when the pod is deleted by the replica set or evicted by a node drain, the hotel staff comes in and completely empties the safe. The data dies the exact second the pod dies. It provides zero durability.
Which brings us to host path. To stretch our analogy, a host path volume is like the hotel manager allowing the guest to store their belongings in a specific drawer down in the hotel's basement, the basement being the physical worker node's underlying file system.
You are mapping a directory directly from the physical Linux server into the container.
Exactly. This provides a slight increase in durability. If the pod crashes and a new pod is scheduled onto the exact same physical worker node, it can map back to that same basement drawer and access the data.
But there are two massive problems with that. First, if the scheduler places the new pod on a different worker node, the data is completely inaccessible. It is stranded on the other server.
Second, it is a glaring security risk. If a compromised container mounts the physical node's root file system via a host path, an attacker can modify system binaries, steal credentials, and escape the container entirely, compromising the entire host machine. The exam expects you to know why host path is dangerous in production.
So, for true, durable, secure data that follows the pod wherever it gets scheduled, we need an abstraction. We need the persistent volume and persistent volume claim architecture. The guide focuses intensely on this binding relationship.
Why does Kubernetes implement this decoupled two-step process? Why can't a developer just define the cloud storage drive directly in their pod manifest?
It is about the separation of concerns between infrastructure administrators and application developers. A developer writing code shouldn't need to know the complex API calls required to provision an AWS Elastic Block Store volume or the specific mounting arguments for an enterprise NFS array. They just know their application needs a 10-gigabyte drive to store images.
The cluster administrator, on the other hand, understands the physical infrastructure. The administrator creates a pool of persistent volumes, or PVs. Think of these as massive storage units on the outskirts of town. They represent the actual physical storage capacity in the data center or cloud provider.
So the PV is the physical reality. It has a set size, a specific storage class, and specific access modes.
Right. Now the developer writes a persistent volume claim, a PVC. The PVC is just a ticket, a request. It declares, I need a storage unit that is exactly 10 gigabytes, and I need to be able to read and write to it.
The developer submits the PVC ticket. The Kubernetes controller manager sees the request, looks at the pool of available PV storage units, finds one that satisfies the criteria, and securely binds them together.
Yes. And the critical part is how the pod mounts it. The pod manifest never references the physical PV, it only references the PVC ticket.
If the pod is deleted, it checks out of the hotel. But the data remains completely safe in that storage unit across town. A week later, when a new pod spins up on a completely different worker node in a different rack, it simply presents the same PVC ticket, the cluster reattaches the same physical storage unit, and the database picks up right where it left off.
Now, we need to dive into the technical specifics that dictate how that binding happens, specifically the access modes. The guide lists RWO, ROX, and RWX. These acronyms govern concurrency, and the exam will test your understanding of hardware limitations. Let's start with RWO.
RWO stands for Read Write Once. This is the most common mode for standard block storage, like a cloud provider's virtual hard drive. It means the volume can be mounted for reading and writing by exactly one worker node at a time. If pod A on node 1 mounts it, pod B on node 2 cannot mount it simultaneously. It is physically impossible for a standard block device to be written to by two different operating system kernels at the same time without catastrophic data corruption.
What if I have a massive data set, maybe machine learning training models or a vast library of static images? That needs to be accessed by 50 different web servers simultaneously.
Then you need ROX, read-only many. Multiple worker nodes can mount the volume concurrently, but strictly for reading data. No one can write to it. This is highly efficient for distributing static assets across a cluster.
And the holy grail of shared storage, RWX, read-write many.
RWX allows multiple worker nodes to mount the volume and write data to it simultaneously. But you cannot do this with a standard block drive. This requires a specialized storage backend that understands network file locking and concurrent access, like a network file system share, or a managed cloud file system like AWS EFS. The exam will trick you by asking you to bind a pod to an RWX volume using a storage class that only supports block storage, and you have to recognize why the claim stays in a pending state.
What happens at the end of the life cycle? The developer is done with the project and deletes the PVC ticket. Does the physical PV storage unit get wiped out?
That is dictated by the PV's reclaim policy. If the administrator set the policy to retain, the PV changes to a release state when the claim is deleted. The data is preserved, but the volume cannot be claimed by anyone else until the administrator manually sanitizes it.
If the policy is set to delete the exact moment the developer deletes the PVC ticket, Kubernetes issues a command to the underlying storage provider to permanently wipe and destroy the physical volume. It is highly automated, which can be dangerous if configured incorrectly.
Speaking of automation, the guide details storage classes. This feels like the modern evolution of storage administration. In the early days, administrators had to manually provision dozens of PVs ahead of time so developers wouldn't have to wait. That seems incredibly inefficient.
It was. Storage classes introduced dynamic provisioning. A storage class is essentially an automated blueprint. It contains the parameters for communicating with the underlying storage provider's container storage interface, or CSI driver.
Instead of pre-provisioning physical drives, the administrator creates a storage class. When a developer submits a PVC, they simply name the storage class. Kubernetes intercepts the request, dynamically reaches out to the cloud provider's API, provisions a brand new hard drive of the exact requested size on the fly, creates the PV object, and binds them together in seconds.
The level of hidden orchestration is staggering. But there is a topographical challenge here. The guide highlights a specific parameter called volume binding modes, specifically pointing out wait for first consumer.
Yes. Consider a multi-availability zone cloud architecture. You have worker nodes in Zone A and Zone B. A developer submits a PVC for a dynamically provisioned drive. The storage class immediately creates the physical drive in Zone A.
But what if the scheduler, based on resource availability or node affinity rules, decides to place the pod in Zone B? The pod spins up, but a physical hard drive in Zone A cannot be attached to a server in Zone B. The pod fails to start.
A race condition between storage provisioning and pod scheduling.
Exactly. Wait for first consumer solves this. It tells the storage class, acknowledge the PVC request, but delay provisioning the physical hard drive until the scheduler actually decides which node the pod will run on. Once the pod is scheduled to a node in Zone B, the storage class provisions the drive in Zone B, guaranteeing physical proximity. It is a critical optimization for highly available architectures.
So if we look at the big picture, we have built a resilient control plane, deployed stateless and stateful workloads, engineered complex Layer 7 routing and network security, and established durable, dynamically provisioned storage. The system is humming.
Until it isn't.
A deployment fails. A node goes offline. A database refuses to connect. And that brings us to the final and most heavily weighted section of the deep dive, Section 6, the firefighter. Troubleshooting.
This accounts for 30% of your score. It is the make-or-break domain. The theoretical knowledge we have discussed up to this point is foundational, but here, theory goes out the window. You must become a forensic mechanic. Because it is a performance-based exam, you aren't answering multiple-choice questions about how you would theoretically fix an issue. You are dropped into a broken cluster, given an objective, and told to repair it under the ticking clock.
The guide logically breaks troubleshooting into layers: cluster and node issues, pod issues, and networking issues. You have to isolate the blast radius. Let's start at the lowest physical layer. A worker node is malfunctioning. The scheduler isn't placing pods on it, or the pods currently on it are crashing. What is the forensic workflow?
You start with a macroscopic view. You run stitch starts. If a node is reporting a status of not ready, the problem isn't Kubernetes. The problem is the node itself. The API server has lost communication with the local agent, the kubelet.
So you have to leave the comfort of the API and descend into the Linux operating system. You SSH into the specific worker node.
Precisely. Once you are on the node, you rely on standard Linux system administration tools. You run system-tab status kubelet to see if the process is actually running or if it panicked and crashed. If it's dead, You use journal TLS kubelet to read the system logs.
And what are you looking for in those logs?
The exam will often simulate misconfigurations. Perhaps someone edited the kubelet configuration file and put a typo in the cluster DNS IP address. Perhaps the node's swap memory was accidentally re-enabled during a reboot, causing the kubelet to refuse to start. The journal data logs will give you the exact line number of the configuration error. You fix the typo, run systemtitle restart kubelet, and watch the node status flip back to ready in the main cluster view.
But what if the node is ready, but workloads are still failing to schedule there?
Then you look at the node conditions. The kubelet constantly reports its health back to the control plane. You run to its described node, and you look for conditions like memory pressure, disk pressure, or PID pressure.
If a node reports disk pressure, it means the physical hard drive is filling up with logs or unused container images. The kubelet acts in self-defense. It applies a taint to stop new pods from scheduling, and it begins violently evicting running pods to try and free up space. You have to identify what is consuming the disk, maybe a runaway application logging in debug mode, and clear it out.
Okay, so the hardware is healthy. The node is fine. Let's move up a layer to the workloads. The guide highlights 3 specific pod status states that you must be able to instantly recognize and diagnose: pending, image pull back off, and crash loop back off.
Walk me through the diagnostic tree for each. We talked about pending earlier in relation to scheduling.
Right. Pending means the pod object was successfully written to the etcd database, but the scheduler cannot find a home for it. The pod is stuck in the waiting room.
The diagnostic tool here is always a describe pod. You scroll to the very bottom to the events section. The scheduler will explicitly tell you why it failed. It will say, 5 nodes are available. 3 nodes have insufficient memory. 2 nodes have matching taints that the pod does not tolerate. Your fix is either to lower the pod's resource requests, add the missing toleration, or scale up the cluster hardware.
Next is image pull back off. The pod got scheduled, but the container refuses to start.
This is a failure at the container runtime interface level. The kubelet asked container to download the container image, and it failed.
Again, you look at the describe events. The most common cause is human error, a typo in the image name. The guide specifically mentions spelling Nginx as Nginx. If the repository doesn't exist, it fails. The other common cause is authentication. If the image is in a private corporate registry, the worker node needs credentials to access it. If you forget to attach an image pull secret to the pod manifest, the registry denies access, and you get an image pull back off loop.
Here, finally, the most notorious error in Kubernetes: crash loop back off.
This is the most complex to diagnose because the infrastructure did its job perfectly. The pod was scheduled, the image was downloaded, the container started, and then the application code inside the container threw a fatal error and died. The kubelet sees the process exit, restarts it, and it dies again. It enters a continuous loop of crashing and backing off.
The infrastructure is fine, the app is broken, so describe won't tell you the whole story. You need to look at the application's standard output.
You must use klog's pod name. This intercepts the standard out and standard error streams of the container process. You are looking for application-level stack traces. Maybe the application is trying to connect to a database hostname that doesn't exist. Maybe it requires an environment variable that was forgotten in the deployment manifest.
And crucially, if a pod contains multiple containers, say an app container and a logging sidecar, the logs command will fail unless you append the DAX slag to specify exactly which container's logs you want to read.
Okay, so we've isolated node issues and pod issues. But the most insidious problems are networking issues. A pod might be running perfectly, its logs are clean, but traffic simply isn't reaching it.
This is where having a rigorous mental flowchart is essential. The guide provides a checklist. I want you to walk me through the exact sequence of steps you take if an exam question states, users cannot reach the web application via the web SVC service. Where do you start?
I approach it systematically from the inside out, eliminating variables one by one. Step 1. Is the compute actually healthy? I check the pod status. If the pods are in crash loop back off, the network is irrelevant. The application is dead. You have to fix the app first.
Step 2. If the pods are running, you check the service definition.
I run commando describe SVC web SVC. I am looking for configuration mismatches. Is the service trying to route traffic to port 8080, but the container is actually listening on port 80? If the target port doesn't match the application's actual listening port, the traffic hits a dead end.
Step 3. And this is arguably the most common pitfall in the entire ecosystem.
Yes, the endpoints. Remember, a service dynamically discovers pods using label selectors. If the service is configured to look for pods labeled app web, but the deployment was accidentally created with the label app frontend, the service will find 0 matching pods.
You run cunny, get endpoints WebSVC. If the endpoints list is blank or says none, you have a label mismatch. The service has no idea where to route the traffic. You have to edit the service or the deployment so the labels perfectly align.
Step 4. The endpoints look good, the IPs are listed, but the application still can't communicate with the backend database service.
Now I test internal DNS. I will spin up a temporary disposable BusyBox pod inside the cluster, open an interactive shell, and use a tool like nslookup or reget to try and resolve the service name directly.
If read your web SVC fails with a name not resolved error, but reget if address of service succeeds and returns the web page, I know I have a systemic DNS failure. I immediately exit the test pod and go investigate the CoreDNS deployment in the kube system namespace. Are the CoreDNS pods crashing? Is the CoreDNS configuration map corrupted?
Step 5. Pods run. Service matches. DNS resolves. Internal connectivity is flawless, but external traffic from the internet is still dropping.
That is when I look at the security perimeter, network policies. I check to see if a newly applied network policy has enacted a default deny rule on the namespace, effectively severing all ingress traffic before it even reaches the pod's network interface. You have to review the active policies and ensure there is an explicit allow rule for the specific port and namespace you are trying to reach.
That systematic elimination of variables, compute, port mapping, selectors, DNS firewalls, is the only way to survive the troubleshooting section without losing your mind. And the guide rounds out the toolkit with one final, incredibly powerful command, parquet exec.
Exec is your ultimate diagnostic tool. It allows you to drop a live interactive shell directly into a running container. If you suspect an application is failing because a persistent volume mounted incorrectly or a configuration file wasn't injected properly, you don't guess. You run kexec at pod name binge. You step inside the container's isolated file system, navigate to the directory, and look at the files with your own eyes. It bridges the gap between orchestration and traditional system administration.
And that comprehensive diagnostic toolkit brings us to the end of the technical domains. We have unpacked a massive amount of architecture today. To summarize the path to passing the CKA, it begins with an optimized environment, setting your aliases, mastering auto-completion, and leaning heavily on imperative dry runs to generate perfect syntax.
It demands a deep structural understanding of the control plane architecture, from the API server's gateway to CT's consensus mechanisms, and the strict lifecycle management of kube ADM upgrades and backups.
You must master the granular mechanics of workload scheduling, the complexities of Layer 4 and Layer 7 networking, and the decoupled abstraction of persistent storage. And above all, you must be a forensic mechanic, capable of systematically troubleshooting broken components under intense pressure.
But understanding the theory is only half the battle. Before anyone attempts this exam, the study guide provides a highly recommended, actionable directive. You must practice in a live environment, utilizing platforms like Killer Coda, which offers free browser-based scenarios, or the killer.sh simulator provided with your exam registration is non-negotiable. Do not take the exam until you have built muscle memory on these platforms. You need to be able to execute the workflow, investigate, dry run, modify, apply, verify fluidly without stopping to think about the syntax.
Muscle memory is the only thing that will carry you through when the 2-hour clock is blinking red. Which leads me to a final thought for you to chew on as you prepare. This exam is entirely open book. You have full access to the official documentation. The definitions and the YAML structures are quite literally at your fingertips. Yet, the CKA maintains a notoriously steep learning curve and a high failure rate.
What does that reveal about modern IT operations? It demonstrates a fundamental philosophical shift in our industry. It is no longer about the rote memorization of commands or knowing what a technology is. It is entirely about applied critical thinking, recognizing structural patterns, and navigating complex, interconnected failures under immense pressure.
When you spin up those practice clusters and intentionally break them, ask yourself, are you merely studying to pass a certification test, or are you actually simulating the inevitable 3 a.m. production outage?
You are training to keep the system running when everything else is failing.
Keep your aliases short, rely on the dry runs, and we will see you next time.